Paul mentioned, my name is Vikram Gupta. I'm a senior director here for any things that are related to the product, the definition, the design, work with Gary closely in figuring out what we want to build next. So I think you heard a little bit of what we are doing in the next 8 to 18 months. So let me bring you back as to what people are able to do today with the product, and especially around when you are storing a large amount of data. We have customers as small as few hundred terabytes and as large as a couple of petabytes, right? So, and the philosophy is you buy commodity hardware from HP, Quanta, you name it, and put the software on it, and it smells and behaves just like Amazon S3, right? So, so we have obviously solved the challenge around on the cost side, on the scalability side, right? So if you look at some data, I mean, there are different ways of slicing. Like what the cost of storage has been traditionally from some of the big, 3 or 4 vendors. It's been the storage software or the storage hardware, which was very hardware defined. But as you go towards a model which is more software defined, the prices have started to go down. There are companies like ours who are able to prove that you can actually now deploy software at almost around 1 cent per gig per month, type of model, right? Which is where Amazon actually came in and changed the whole landscape. But I think as you see, when the hardware cost actually goes down, the operations certainly becomes a focal point, because now the dollars you have to justify. Do you want to spend the time in there, right? Few hundred, one way of looking at it is from I think Gartner was around. Traditionally, we were managing around 300 or 400 terabytes per full-time engineer. But as the data is growing, I mean, how many people will you need to manage, let's say, a petabyte system, or 2 or 3 or 4 petabyte systems, right? So we get in deals or RFPs where even 1 petabyte is not enough, right? People are talking large amount of data that is geo-distributed, right? Nobody's putting all the data in one data center. So certainly this whole equation becomes complicated.
So that estimate, is that from Gartner? You're saying that's from Gartner, that estimate?
Yes.
One full-time 344 terabytes of what type of data? Because management of file, block, object, very different from the amount of effort you have to put in. And also, I think that number's way too small. I think that's been a lot bigger for a lot of.
Again, I think we can debate on the numbers, but I think the point here is whether it is 400 or 500 or 600, I think we are talking in a completely different range, which is a couple of petabytes, right?
Yeah. So I'm not questioning your value. I'm questioning Gartner.
Absolutely. So yeah, there are different ways of slicing.
Gartner's, just a little background on that. So this is their latest analysis, 2016, January 2016. They do an IT metrics analysis. They interview lots of IT departments, and so you're getting back feedback from each IT department. So best of what we could guess in terms of the numbers of what it is, but I think we need this factorial change, right? We need to really change, how do we manage at scale, and it needs to be tenfold what we can do today.
I used to do a lot of analysis of people's environments, and one metric we used to capture was the number of FTEs they had managing their environment.
Oh.
That's why I think that number is low. That's the only reason why.
Yeah.
So I think so our focus for last 6 to 8 months and going to the next 6 to 18 months is all around operations. I mean, we know how to store data, we know how to distribute it, we know how to make it durable. Now the question is how complex it's going to be. Everybody can deploy software, but suddenly when disks are failing, when hard disks are failing, or systems are failing, who you point to, how you replace drives become very important. So our goal is, can one full-time engineer manage 15 petabytes of data? So obviously it's a long way to go there, but I think we have reached we have reached a milestone in terms of figuring out what are the common tasks. When we talk to our customers, what are the things that should be made simple? And if you look at it, ultimately, these are some of the driving principles that when we talk to some of the largest customers or systems that are run by Googles or the Facebooks of the world. What are they, right? So number one is smart operations, and what we mean by smart operations is machines and algorithms are much better in doing repetitive tasks and smarter things as opposed to humans doing them continuously. So we want to remove or eliminate most of those tasks so that you're not doing that on a day-to-day basis. For example, making the user interface simple, making it available on different devices, right? automating the operations that are very cumbersome, time-consuming, and repetitive. Right? Storage analytics. We are starting to embrace storage analytics, which is different from the app analytics, which is about can the system start to give more detailed information where you can focus on making decisions rather than just collecting the data, right? And I'll show you some tidbits on that. And I think at the end, self-service consumption model, right? One of the things I like about Amazon is it's simple. You want 1 terabyte, you want 100 terabytes. It's literally a click of a button and you get it, right? It's the machines are provisioning it for you, right? So make the operations completely smart. Durability, again, it's table stakes. I mean, your system has to be durable at scale. So always on, always repaired, always verifying what the system is doing, right? Automating around how to avoid failures and things like that. And then finally, I think the final piece to this puzzle is about a change in the whole support model. Where again, machines are looking at telemetrics data, they're trying to understand what the anomalies are, what the problems are, and identifying before they can occur or before they can create an outage of the system, right? So we'll touch upon all of these and how Hyperstore is making the daily life of our administrator much easier. So let's talk about simple user interface, right? So I think since last we met, we have done a lot of work in simplifying the UI. I mean, everything is programmable, we talked about, but there's a whole class of people who are looking for simplicity. I mean, my classic example is Apple phone versus Windows phone. Like Windows will give you all the knobs to turn on a wireless, and then you're still struggling with it, versus an Apple phone which makes it easy. But on the same point, if you want to go into the weeds and you want to go and look at the system, you have the ability to go inside different pages, right? So we make it simple. And we'll give a demo of that to begin with. Visual analytics. I think this is the chart that we showed you. For a lot of times our customers are asking, okay, I have 20, 30 nodes distributed across different data centers. I just want to know how my data center capacity is spread around, right? So we use this graph, which basically starts from the left, shows you the total capacity, then it breaks down into the data centers, right? We allow customers to have asymmetric data centers. You don't have to have equal number of nodes on each and every data center. You can have 1 petabyte in Los Angeles, you can have 500 terabytes in a different data center. Depending on the policy, we'll pick and choose how you want to distribute the data. Yeah, and then once you pick a data center, then it actually gives you a little bit more detailed view on every node. So you can see where the hotspots are and things like that.
Yeah, and also asymmetric nodes. So every node can be different sizes. We dynamically rebalance the key space based on the different nodes in the environment.
And that is important is because when you look at the pace at which the servers are innovating, right? I mean, you can find a 12-node server, you can find a 24-node server, you can find a 36-node server, depending on the class of or the type of hardware that the customer want to choose. The software automatically adapts to that, right? So giving views like these.
So you could roll in a new server and roll out an old one. So yes. You could use it as a rolling upgrade method.
Yes. I mean, I use the analogy of the pet versus cattle, right? I think you guys have heard that. Where servers from our perspective are unreliable resources. They should be able to go in and out of the system, and the software should be reliable to make sure your data is safe. Okay. Again, this is actually one of my favorite ones. So here you are actually seeing 50 nodes or around 25 or 40 nodes here, where we wanted to, when we talk to a lot of our customers, they have monitors where they want to see their large cluster alerts or monitor them in a much easier fashion rather than having lists of pages and
this is such a clever layout. That's right? One of the things I look at and so wow, and that's really well thought out.
And then we change the colors. So I mean, we literally have a customer in San Diego which has a giant monitor, and the guys are literally seeing if the color changes. He can go and click on individual node and focus on that, right? So I'm already bubbling and making sure and making it intuitive for you, so that when you're spending time going between different graphs, right? So and you by adding node is also made very simple. You can literally come here, click the plus button. The only thing you have to do on the node that you want to provision is provide an IP address and put our software bits on it, and come here and provide that IP address, and we'll show you a demo on that. And it basically takes over from that, right?
We do that internally because we use Puppet as our means for distributing updates across the entire cluster. We actually use a multi-master Puppet server as a way to manage distribution of content and objects, config changes across the cluster.
Now, obviously, making complex things simpler is is a cool thing. But actually, keeping simple things simple is also key. And here is another thing that we did was, obviously we deploy on any type of hardware. We also provide customers a turnkey solution, which is literally a Supermicro or a Quanta or a Dell or a server where we install our bits. But we make sure that other than being just software defined, you also have simplicity in terms of doing basic tasks. We have a customer who had 600 drives, and if a drive fails, if you look in the software, it will tell you on this machine a dev 13 has failed. The question is now, how do you go from there to going and replacing it? Do you need an expert to go and figure out and run shell scripts, or do you want a guy who would literally go in and look at a blinking light and change it, right? So we basically wrote it using open tools, simple methods where you can blink a server, you can blink even a drive, that if it's in a JBOD or if it's a server, right? So you have simple buttons over here which will tell you the type of server it is on, and you can literally click a button if a drive has failed and it will blink it. So you basically have to just go identify the server and open the tray and take the disks out, right? So a lot of so making tasks that can be lengthy, keep it simple and minimal, right? It's completely brain dead in some sense. Obviously, I think again table stakes. You don't expect a petabyte system to go down over a weekend because you have to do an upgrade, right? So because we are completely software defined, we use everything in user space. Making the system upgrade is key part of the system, right? So we slowly go and change and upgrade each node at a time in the background, so you don't have to bring the system down. Okay. This is Akina, my second favorite one, and this is actually we spent a lot of time around is when you have, let's say, a petabyte, 2 petabyte, 3 petabyte system, the probability math, if you do, the number of drives will actually fail a lot faster just because you have that many number of drives. Now the question is, we all have erasure coding, replication, and different schemes to make it sure that the data is rebuilt. But at any given point in time, you want to have visibility around what's going on, right? So we built this page to show you what is going on in the system. We have on the top left, you will see, and we'll talk about proactive rebuilds. So rather than like in the old days of RAID, where when the RAID disk fails and you're running around and putting it in and trying to rebuild the RAID, we have gone and moved on from that, where the system automatically detects the problem. If you have enough drives, it will automatically pick a drive and rebuild the system, right? So you're not, my favorite example is you're sitting in Friday with your family having dinner and a drive fails. You do not have to panic. The system will automatically pick a drive, move the data, rebuild the data, and send you an email alert.
So are you saying that you're doing that on a hard drive failure or a soft drive failure from Smart?
So we do it on a hard drive failure.
Okay. You're not doing it on a soft threshold that you've determined through Smart that says, I think this drive might fail in
We are.
5
We do.
minutes.
We do on
You are
both
doing
sides.
that?
Yes.
Yeah.
Both software intelligence and the hardware
And
intelligence.
how do you work out what the threshold is for working out what a Smart level failure is?
Do you remember what our
Is that-
threshold is right
we
now?
don't use the Smart utility, if that's
Okay.
what you're referring to. If from the application level, if you could configure how many write or read failures have occurred from our system, and then mark it as down.
Right. So can the customer tweak that?
Yes,
Define
it's
that, yes.
configurable.
So
Okay.
if you thought you were getting a lot of failures, and are you then keeping logs of each of the drive types? So you could go back, for instance, as a correlation. Imagine you had a very large environment which had hundreds of nodes in it, and you started to see a certain drive type fail. Can you?
Exactly.
Will you keep a log of that in terms of failure, so you can go back and?
Well, we have
drive-
all that disk information, the device ID,
Right.
the serial number, and so on attached
So
to
you
it.
could do
yes.
that.
But what we haven't done is added the analytics. I really like
Well,
the idea. It makes a heck of a lot of
This is the
sense.
point, isn't it?
scale.
Because
Yeah.
Right.
ultimately, if somebody sees something happening and they know it's a particular drive type, there's two benefits. One, everybody else can be told about it. Two, you can then look at your risk and say, we've got a risk on half of these nodes because we've got those drive types. in there.
Absolutely.
Absolutely.
And then you can
A
look
lot
at your
of
own
sense.
risk profile
Correct.
a bit better.
Absolutely, right? And then you have the same beehive here, and we do different types of activities. We are either proactively rebuilding it, or when you're commissioning, decommissioning nodes, you're rebalancing the data because you have added system, right? So you have a data rebalancing status up there. So you can instantly look and see what the system is doing, so that you get and the idea here is to give you a peace of mind that the system is working for you, right? And there are points when we will alert you, we will need some decisions to be made. You come to the system and you make the decisions, but you get a complete on-the-spot view of what the system is doing, right? And then finally you have the data integrity check, which basically again checks for bit rots and things like that. So if you have systems running for, let's say, 3 years, you want to run bit rots checks on it just to make sure the disks are not annoying on you, right?
Yeah, and a lot of it, I mean, this is built by feedback from our customers, right? I mean, you got a lot of automated things going in the background to make sure the data is always durable, we're rebalancing things, but they wanted to see what was going on. They're an administrator, they're a storage administrator, they still need to be able to see what's happening on their system, how is it performing, what are the different data operations, and so that's why we built out these kind of screens and extensions to it.
And obviously, if on a good day, everything should be green. So, right. So we change the color of the cell again to show you who's participating in what. So somebody's participating in proactive rebuild, somebody's doing rebalancing, and then if you're running a rebalancing, it tells you how much it is done, how much is about to finish. So you get an estimate of what's happening in the system, right? So I'm going to switch gears and talk a little bit about durability and some of the innovations that we have done around the space. So a traditional object storage system basically has, I call this a more of a reactive repair or a rebuild. And what it does is, because it's a system where everything is flat, you don't have a hierarchy like in NAS systems. You don't actually keep state of on any single machine how much data is spent. So I use this analogy is if a drive actually fails, object storage system, a good object storage system which can scale to a very large number of items, you actually have no idea where the data actually of that object resides, because everything is algorithmically done. You don't have the lookup effect that you have in NAS systems. So the problem with that is, if you don't know where the object or the copies of these objects are, you actually have to scan the system and then once identify where the system is or what objects needs to be repaired. You actually initiate the repair. So in small system is good because you can quickly do that scan. But when it gets bigger and bigger, this problem gets actually worse, because you're now scanning a larger system and there's a lot of disk IO activity happening, right? So this is we call as more of a reactive rebuild, because that's what you need to do. So you're spending a lot of time on doing and just scanning and identifying. The analogy here is you're on a beach, you are looking for that coin, and you're just scanning the whole damn thing, right? So what we did is when we talk to our customers and they say I need an ability to, when the disk has failed, and to make this system highly durable, right? So what we did was we actually took a very simple approach, and the approach is whenever we see an error, right, we actually drop these hints in Cassandra. And what these hints basically are is just, I saw an error, I couldn't reach this system, I couldn't reach that drive, I couldn't touch this network. We actually drop that flag, and the normal IO system keeps moving on, because you either have two or three replicas or you have erasure coded systems. But the guy who's actually rebuilding, rather than waiting for 10 days or 30 days or a month, he can actually now pick up and run on each and every node and look up these hints and start the repair process. So it's more like a map where you have these hints, and you knew that there was some problem that had occurred over there. There's another hotspot where we saw the problem, and so the repair or the rebuild process is actually more actively running. We're running our repair actually every 15 minutes to basically identify where these errors have happened. So my scan time actually is completely gone, because now I have these hints that basically tells me where to focus on, right? So if a drive or a network glitch or a power outage has happened, certainly all my repairs will start showing up on that side, as opposed to scanning the whole system. And that too, again, remember, whenever you are geo-distributed, everything becomes super complicated, right? You don't want to move around things like that. So again, it's completely opposite of that, right? It's parallel. The bigger the system gets, the faster it actually repairs, right, as compared to the old system. And then your window of redundancy reduces down, because you're now down to 15 minutes or something like that, right? Another approach, I think simple approach we did was, if you are on an eventual system, which is what object storage systems do, whenever you are putting the object, there is a point when your system will catch up. And here is an example of a put, and when you're doing a get, the third node which hasn't caught up yet has to go and fetch the data from the other side. And again, you have 2 copies rather than 3 copies, right? So what we actually think is, again, to make the system extremely durable, how can we use this opportunity to catch up? So what we did, again, a very simple, clever thing. When the data is actually being retrieved, when this third node gets the data, he's basically behind a queue, and you are waiting for him to catch up. And we actually literally just change his position, bring him up. So you're actually rebuilding the copies of the data that's actually being fetched, right? So again, use every opportunity to bring the system up to date as much as you can. Here's another example, a simple example, a very clever trick. In Creature coding, you have a K plus M, like in a concept. For example, you have K fragments for data, M fragments for parity. Whenever you are doing a put, let's say, right, the system will ask you, I need, let's say, 4 plus 2. I need 6 nodes to write the data. The problem that we started seeing is, as long as you can sustain 2 failures, the system is great. But if you had a 20 node system, and let's say a node that was actually experiencing network glitches or network problems, when you ask for the 6 nodes that need to be used for writing the data, you basically try to issue the write on it, right? And if a node that is not responding or was not able to answer your queries, you basically keep moving on because you're on an eventual system. But what again we did was, rather than asking for K plus M, we basically again asked for K plus M plus L. L basically here are like hotel nodes, right? So if I was supposed to write on these 3 nodes, and this 3 nodes, while I was doing my transaction, something happened to it, I keep moving on. And rather than waiting for this guy to come back up, I'll basically get the data written on this node. So again, during the IO process, I'm making sure my debt to repair or bring the data back in consistent state always remains small, right? So simple tricks like these really makes the system very scalable without complicating the architecture, right? This is another actually patent pending technology that we built, and the idea here is that if you have a key space where all the data gets chopped in, and you basically assign in what node certain amount of data will reside. So you have a static mapping traditionally in most of the object storage systems, where you will say this is my token space. All these portions of this token will map to a certain node. But there are cases where, for example, you may have imbalance or you may have disk failures. So in this case, you're seeing that either at time t0 or t1, the blue mapping remains constant because it's a static mapping, and it's the operator's responsibility, if that node or a disk fails down, to move those tokens or bring those systems back into the consistent state. But again, the model is, if you're having dinner at 9 p.m. with your family, you do not want to get up and go and figure out what needs to be done, right? The system should be intelligent enough that I have enough resources in the system, I don't just keep moving on, right? So what we did was we invented it's kind of like a snapshotting technology, if you look at it from a traditional perspective. But what we do is, if we detect any anomaly on that resource, we actually automatically move the tokens internally. So this blue space, for example, if you either have an imbalance or if you have a disk failure, automatically gets mapped to other systems in the node. So the beauty of that is, when a new IO is coming in, it automatically bifurcates and goes to the new devices or new nodes. So that device, if it has caused any problem, is completely shut off from the system. The only thing that you need to do from that node's perspective is, or that hardware perspective is, rebuild the old data. All your new data will continue to be still durable.
Do you have to then? Does that mean you can have nodes that have different disk types and different disk parameters in them? So, if I bought some 2 terabyte ones, I could put 6 terabyte ones in the same chassis and just let you automatically work out where to put stuff. So
ideally, you want to, again, to keep the balance of the cluster.
Great,
yes, you want to keep the types of the drives within a node to be similar. But you can have a node with 6 terabyte drives and a node with 4 terabyte drives.
You couldn't mix the drive types within a single node.
No, it's just from an operation. Yeah, operational complexity, right? Yeah, we don't do that.
Fair enough. Just because that's an upgrade path, isn't it? Pulling nodes out of a
correct.
Not a great one, but it's it's.
Yeah, but So, and then lastly, I think before we go to the demo, I wanted to touch upon this the bucket backup and restore functionality. Now, we have customers who will basically store, okay, I've got a petabyte of data on you. You guys are great, but what if something happens, right? So I need a protection mechanism. I can replicate everything, but still, right? So we basically actually use the same technology that Amazon actually released, and they call it the CRR. It's called cross-region replication. And what it does is very simple. You basically have two clusters. All the puts in the original cluster are basically mirrored on another cluster. Okay, these are two independent. They could be of the same version. Obviously, you don't want to do that. You may have one on 6.0, one on 5.0, just so that you don't want to put all your eggs in one basket. Or you can actually have one on Hyperstore and another on Amazon. Again, hedging your bets. So all the puts that are going on us will get replicated or will basically be replayed on another cluster. The catch here is that when the deletes happen, we don't propagate those deletes, right? So the beauty now is I can give you a secure vault kind of use case where, example, your original cluster can be your day-to-day use, but second one can be your secure location where everything is getting pushed there, but nobody can delete any data out of it.
How does that work with versioning? Because obviously, if you've got versioning enabled, the delete is effectively just typed.
So this actually technology requires versioning to
right,
be on.
you do have to have that on.
Yes, right? And then, so as you see here, when a delete comes in, we just basically put a marker there saying the delete is done, but we never delete the data. And then, obviously, when you have backed up everything, you need a restore capability. So we provide a restore capability where you can say, hey, I want to restore this data or this bucket or this object from this time. So we will automatically take the data out from your backup bucket, right? So again, the use cases where people are starting to use this is my original cluster could be a replicated cluster because you want to do everything on a daily basis, and the second one could be an erasure coded, which is a lot more cheaper because you can actually build two different systems completely independently.